All right, so here we are again, AP test review number 4. Just numerical integration, a lot of rectangles, trapezoids, and then some AP style questions that have been asked over the years with these. So the first few here, just a little review, general ideas, big picture things that get used in a variety of ways as we moved forward from this point throughout the year. But the first couple, just your definite integral from 0 to 6. This is f. We want to integrate f to find a value, an average value, and then an area. All of these, whenever we're talking about an integral is how we can accumulate change. When we're doing that with a graph, it's simply the area underneath, but we just want to distinguish between, especially these two, the value and the total area. So if we do these areas, this has an area of 10, but it's underneath the x-axis, so it has a value of negative 10. This would be a negative 5, positive 5. This would be what? 20. And then this would be 5. If we do value and area, we just need to know what the difference is here. Look at our graph. We've got 30 units of area above the x-axis. We have 15 units below the x-axis. Value is your net change. So if we were to combine these, the 30 to the negative 15, the value is 15. If we want the total area, then we're not concerned about our sign. We're just looking for how much area do we have. So that would be 45. It's like an absolute value idea. The average value would be this thing. So we'll see this a little bit today. This is the average value of a function. So we've already done most of the work for this. We would just do 1 over 6 minus 0 multiplied by what we just found the value of this to equal. It should be a 6. And the value of this from up here would have been 15. So we simplify that. Our average value would have been 5/2. Idea value versus total area is the big one. And we just need to make sure we know which one we're looking for. So with this, I'm going to do just for, let's review this a little bit. So it says using this integral, so you're given the integral, x squared plus a 4 from negative 2 to 2. You're going to use 4 left endpoint rectangles. So if we sketch this in, have a y-intercept of 4, parabola opening upwards. We want to approximate the area from a negative 2 to 2. We want 4 rectangles. So the way I got those values is the first thing we always have to figure out is what is our base. And our base is our change in x, and that's always b minus a over n. So our base for this problem is the change in x. The difference in the interval would have been 2 minus a negative 2. I wanted 4 rectangles. So the base of this, which is our change in x, is 4 over 4. That's a 1. So that's how I knew. I'm just going from negative 2, negative 1, 0, and then from 1 to 2. This should give us 4 rectangles. So here is going to be rectangle number 1, rectangle number 2, 3, and then 4. We want them to be left endpoint rectangles. So that means we would have gone up from the left side, touched the curve, come on down for all of them. What we also then would have talked about at some point, these are also circumscribed on the left. So rectangle number 1 and rectangle number 2 we would say is circumscribed because we go outside the curve. 3 and 4 we would have said is inscribed if we start throwing some of those words around later in the packet. We then would have taken where do we hit our curve. So we would have called that C sub 1, 2, 3, and then 4. And the places where we hit our curve were left endpoints of negative 2, negative 1, 0, and then 1. We can then set up our Riemann sum. So we know we have 4 rectangles. We know we're going to be starting down here. Then we call this K. I know now what we're doing. We're calling them ends. They're interchangeable. Doesn't really matter. And what we were going to be adding is a height times a base. We now know the base of all our rectangles is 1. Our height is our function. This is our function. If you remember, to make it work so that we're plugging in the integers 1 through 4. Instead of x squared plus 4, we call this c sub k squared plus a 4. And then what we're really just doing is adding up a bunch of areas of rectangles. So I'm going to do this below. So for rectangle number 1, we want its height and its base. So its height at this first C value of a -2, we would plug that in. It's really hard to squeeze this in because this pen writes rather large. -2 squared plus 4, that's the height of rectangle number 1. Its base is a 1. If we do the second one, we're touching it at -1. So -1 squared plus 4, base is a 1. And then 0 squared plus 4 times 1. And then the last one, we're back to 1 squared plus 4 times 1. So add them all up. This had an area of 4. This has an area has an area of 8. This has an area of 5. Now this makes more sense. This has an area of 4, and then the fourth one, we are back to an area of 5. We add all those up. Our area is 22. All right. Now I just have to figure out how to erase this on a PDF because that I have not figured out. So give me a minute. I'm going to pause you. Okay, that only took me about 10 minutes to figure that out. But we now have some space to work with our trapezoid rule. So I'm going to sketch out the same curve. X squared plus 4. Still going -2 to 2. We're still going to do this, instead of 4 rectangles, you're going to do 4 trapezoids. We start this the same way. We calculate our change in x. 2 minus a -2 over 4. Our change in x is going to be a 1. But if you remember, that's actually the height of our trapezoid. But we'll get to that in a little more detail here in a minute. Let's go over here. We know we're moving over by 1 each time. Trapezoids are a little easier. We just go up from every single point, hit the curve, connect them, that's a trapezoid. Hit the curve again, connect these two, we have a trapezoid. These two, we have a trapezoid. Those two, we have a trapezoid. So we have our 4 trapezoids like we're supposed to. We have a trapezoid rule as long as we have a common change in x. So we'll revisit some of these here in a minute when we don't, but this has a common change in x of 1. So we can approximate this area with 1/2 times the height. This, make sure you know, this is the height of a the area of a trapezoid in general. You should know that pretty well by the time we finish this off if you had forgotten. 1/2. This is our height. We know that is a 1. Then we do all of our bases here. We had our little shortcut. What we need now is base 1. If you look over here, base 1 is used once, but this second base, the third base, and the fourth base is going to get used twice, and then the last one just gets used the 1 time. So what we need to do is figure out what those bases are. So the way we did that is we went ahead and listed out where we're hitting our curve, similar to what we did in the previous problem. One of the things they have tested on over the years is if I have 4 trapezoids, we have 5 bases. So we should be hitting the curve 5 different spots. -2, -1, 0, 1, 2. Now we want to make sure that these are the bases we're plugging in. These are not your bases. The bases, this is base sub 1 here. I need to figure out what is this length. So I'm just going to take the -2, plug it into the function, x squared plus 4. All right, so again, this is our function, so we're just plugging that in. X squared plus a 4, and that would give us 8. If I wanted the second base, this one here, so this is base number 2. Plug in your -1, that's going to give you a base of 5. Our third base is going to be 4, that's this one. The fourth base, when we plug in 1, is back to a 5. And then our fifth and final base is going to be back to an 8. So again, first base we use once, so you're putting that first 8 in here 1 time. But base number 2 you're using twice, so this 5, oh boy, 5 you're going to double. The third base of 4 you're going to double. The fifth base, or the fourth base of 5 you're going to double. And then the last base of 8 just goes in once. Okay, add those up. We should get 1/2 times 44. And we actually get the same exact answer. These are also approximations. This is not when they force you to use approximations, but these are approximations, so it would be safe to go ahead and do that. These aren't guaranteed to be the same. So we got, did I not give you the answer up here? Did I erase it? I think I erased it. So this is 22 as well. Now, it's nice that these are the same because they should definitely be very, very similar. They're approximating the same area. They're not guaranteed to be the same. But when we try to evaluate a definite integral, that's our two approximation methods, either with rectangles or trapezoids. So having done these two problems now, I can tell you, you won't have to do that on the AP test. I can almost guarantee you that. But this would be very, very, very likely for those with, taking BC. I'm pretty sure you're probably going to get a sequence and series question. And then if I had to guess what that other question is going to be, it's probably one of 2 or 3 topics, and it's this, where you're going to get a table and get a whole series of questions on that. This is definitely something we want to be able to do. Velocity of in miles per hour of a bike rider is measured at random times 0 to 1 hour. The chart shown in number 6. And you're given a table. In a table, we can't find the exact value. We could if we wanted to. If we go back up to here, and I don't want to have to go through this erasing process again, we could just evaluate this definite integral and find the exact area. So there would be no real sense in us doing rectangles or trapezoids. We could just evaluate this, and that'll give us the exact area. It's kind of senseless to do an approximation in that case. Where we have to do an approximation is like number 6, where we don't actually know a function. Like there is no defined function here, so it would be impossible for us to do an antiderivative and find an exact value. So we have to rely on approximation techniques, and that's your rectangles and trapezoids. So in this case, you're going to use 3 left endpoint rectangles to approximate this value, and then it says using correct units, explain the meaning of our answer. We can pretty much do this right now without even finding our answer. If we're going to be evaluating the integral from 0 to 1 of our velocity multiplied by our difference in time, what we are finding here is the approximate change in, what are we dealing with here? Position of the bike rider from the time of 0 to 1 hour. And they say use correct units, so you definitely want to put units over here. And then when we get the final answer, we'll put the unit that we would have for our position. So what we're doing when we do this, we want 3 left endpoint rectangles. You want to make sure you understand this as indicated by the data in the table. The reason that is important, if we try to do our base as the change in x, and we do the whole b minus a over n idea, we would go from 1 to 0, because that's our time interval. I wanted 3 rectangles, so we would say that our base, our change in x, would be a 1/3. But if you look at our table, 0.25, we don't have a 1/3 change. From 0.25 to 0.75, we don't have this 1/3 change, and then 0.75 to 1, we don't have that change. So when it says, as indicated by the data in the table, whether that be rectangles or trapezoids, this is not going to work. These are the ones where we just have to do them all individually. Where if I want to do rectangle number 1 plus rectangle number 2, and then plus, of course, run into here, our third one, we can think of it as 2 different things. The first way we did it is with the idea of area, that we're just taking like what we did up at the top. This is our height, and this is our base. And the base for rectangle number 1, we drew these ends. Here's rectangle number 1. Since we're going to be using left endpoints, our functional value is 21, so that's our height. And then our base, this length right here, would be 0.25. For rectangle number 2, if I drew that in here, here's rectangle number 2, the left endpoint functional value would have been 23. And then the base length, 0.25 to 0.75, is 0.5. So we can definitely approach it that way. We can also approach it now. That's how we did that at the beginning when we talked about all this. We can also deal with the idea of a of calculus now and understanding what the integral is telling us to do. The integral means it's a sum, so that's why we are adding. What we are adding up is velocity values multiplied by our changes in time. So if we do that for rectangle number 3, so look at rectangle number 3 here, up there. The velocity value at our left endpoint is 25. And we are multiplying that by our change in time, the difference in time, which would be 0.75 to 1. So 0.25. That's the other way that we can now do this. When we add all that up, each one of these, now this helps with our units as well. This was a velocity value multiplied by your change in time. So velocity, let's actually use units here, are miles per hour, multiplied by our time unit of hours. So this answer has a unit of hours. All right. I don't know what that is offhand. I don't have my calculator with me, so I'm going to assume you can throw that into your calculator, but whatever that gives you is going to be your final answer. Okay? All right. So next page. Is a similar idea, except you're going to use trapezoids. And then, like we've seen a couple of times, this is asking you to find an average temperature over a certain time period. So if we were to do that, it says, your date and time, whatever, the following temperatures are recorded at various times from 12 a.m. to 12 p.m. Approximate the average temperature over the 12-hour period using 4 trapezoids, as indicated by the data in the table. So that when you read this little phrase means our change in time is probably not going to be constant. If you look at that as not, 12 to 5 is 5 hours, and then 4 hours, 9 to 11 is 2 hours, 11 a.m. to 12 p.m. is 1 hour. So that's why we have to set these up. So now we have to know the area of a trapezoid formula. Oops, that should be a 2. So that's the area of a single trapezoid because we need to do these individually. So let's draw our trapezoids in. So there's one trapezoid, try to make them look like a trapezoid, and we get our 1, 2, 3, 4 trapezoids. So for trapezoid number 1, we would have 1/2 times our height. Our height is our change in x, which for this one would be our change in time. So our change in time here is 5 from 12 a.m. to 5 a.m. That's a 5. And then our bases would be, we touch the curve here, we would touch the curve here, so we want 12 and 13. Plus our second one, we would want 1/2. Our change in time for trapezoid number 2 would be 5 a.m. to 9 a.m. So right in here, that's 4 hours. Our bases would be 13 and 19. For trapezoid number 3, 1/2 times our heights. Now we're going 9 to 11, so that's 2. The bases would be this 19 again with the 22. 1/2. Change in time is going to be a 1, so that's our height for the 4th trapezoid. And then the basis for this, we'd be hitting the curve here at 22 and 29. All right. Now, when we do this, this is not going to make sense numerically. So let me plug that into the calculator. Let me go grab that. So when we plug that in, this would give us 193. That shouldn't make any sense if we're looking for an average temperature. And these were our temperatures, 12 degrees, 13, 19, 22, and 29. Our average temperature would have to fall between 12 and 29. So way too big. If you think about your units, the 5, let's just do the 4. The 4 would have had a unit of hours. If you think about the 13 and the 19, let's say that that is degrees, it's cold, December, so let's say that's Fahrenheit. That's your unit right now. It's a weird unit. It's the product of hours and degrees Fahrenheit. If we're looking for an average temperature, our unit should be degrees Fahrenheit. So the average idea tells us then we want to divide by the number of hours that we covered, which is 12 hours. So that when we now go ahead and divide that by a 12, this answer makes much more sense because it has the correct unit. of 0 degrees Fahrenheit. So what this problem really sets up is this average value idea. We wanted the average value of our temperature. So this would have been, we'll go 0 to 12 just so it indicates 12 hours. When we do the trapezoid rule is approximating this part of the problem. That's one of the ways we can approximate a definite integral with trapezoids. And then obviously the other way is what we did on the front page with a rectangle. That's the 193. But then the average idea tells us that we had to take this 1 over 12 minus a 0, multiply it by the value of the integral, which was 193, and then that would give us this. Okay? All right, number 8, the graph above is the graph of f. If I integrate f from 1 to 3, so I'm just reading this here. So if I go from 1 to 3, if I integrate that, it gives me 2.3. So we want to know integration is area. So when we calculate the area underneath this curve from 1 to 3 in here, we know this has an area of 2.3. Okay? From here to here. I'm trying to write this. Then they tell you that f, which is that graph above, could also be called capital F prime. And then they ask, well, what would regular old f have to be from 0 to 3? So the way we would have gone from capital F prime to a regular old capital F without the tick mark is through integration. So what this is really asking us is, if we integrated f prime, which is the graph above, from 0 to 3, what would that give us? So now that wants to take us from here to here. We already know from 1 to 3 we have 2.3. So if we add on these extra 2 little units here, we take the 2, add the 2.3, should give you 4.3. Okay? All right. Number 9, table of values for continuous functions. I'm actually going to leave you this one. This is the trapezoid rule. We have equal subintervals. This is one I think you could probably do without having to listen to me go through this in an effort to keep this somewhat short. But you should get 13.15 if you wanted to try that. I don't think you would need me to explain that fully through you. It's just another trapezoid rule. So here's all of our trapezoids. We can do the shortcut because we do have equal subdivisions. So check it. Should get 13.15. All right, 10. The graph above is a function, f of x. It is shown in the figure. A sub 1 and a sub 2 are positive numbers that represent the area, so that's important. The reason they're telling you these are positive is because an area is always positive if we're talking area. Then it says, in terms of a sub 1 and a sub 2, what would we get if we integrate that function from a negative 4 to 4? So if we go from here to here, what would that have to give us? And then we're going to subtract 2 times the integral from a negative 1 to 4 with this. All right. So if I go from a negative 4 to 4, so let me do parentheses for this first one, I would have to take the area above, which is this. That is a sub 1. And then I would add it to the area below, which is a sub 2. But since a sub 2 is underneath the x-axis, it's a negative value. Then I would do minus 2. And then I only want to go from a negative 1 to 4. So now I'm only going from a negative 1 to 4. That is also an a sub 2. But since we're doing a value and it's underneath the x-axis, that would be negative. So we ultimately end up with just the a1. And then we would have had this negative a sub 2. If we now multiply this to a positive a sub 2, combine your like terms, and what you would find is we just get a1 plus a2, and it would give us d. 11, pretty big idea. Under normal circumstances, I would definitely tell you this will be on there in subcapacity because it gets at the idea that if we have a Riemann sum, so if we look at this part of the problem here, and then we have our weird root x, I'm going to use k's because that's what we've dealt with in the past, even though they're using i's. And then we do our n here, and then k would equal a1. So we're going to go from 1 up until there. and then we're multiplying that by our change in x. So when we do this, this is an approximation. And the function that it appears we are dealing with is root x. So what it says, on the closed interval a to b, so let's say this is a, let's say this is b. That is going to get partitioned, broken up into n equal subintervals. So let's just cut this in half and then cut each of those in half of width change in x. So like we've done in the past, this is our width. By the numbers x sub 0, x sub 1, x sub n. So those are the numbers that we've always listed. They started with the 0 term, doesn't matter. We would have 4 of them for us. Okay, so we would, let's say we're going right endpoint, rectangles, 1, 2, 3, 4. We would have 4. So these terms that we write down to calculate everything have to fall in between A and B, because A and B is where we start and where we finish. So the big idea, what you want to understand, that will, again, normally for sure test you on this, is that this is an approximation. But if we find the limit of this, as we put more and more rectangles in here, so if you remember the day on the computer, we put on the overhead, if I start jamming more and more and more rectangles in here, our approximation gets more and more accurate. It basically just becomes this continuous sampling of rectangles with no longer having a change in x in between them, and it's a solid shaded region. The limit of our Riemann sum, so if you ever see this guy here, on May 12th, and they want you to find the limit of your Riemann sum as the number of rectangles grow, that's your definite integral. That's what the definite integral finds for us. Our function is now root x. We don't have to worry about the weird root x sub k or x sub I in this case. And then the delta x becomes our dx. We start with a, that's the beginning of the interval we're concerned about, and we finish at b. That could be your answer. It's just if we look at the answer, it's not written like that. You can see they've just had you play this out and finish this problem. So we just do our antiderivative. So that'll be x to the 3 halves. Divide by 3 halves from a to b. Pull out that 3 halves is the 2/3. Upper limit minus the lower limit. And then that will give you a. Big picture idea here that you would get tested on is the idea that the limit of our Riemann sum as the number of rectangles goes to infinity, that then is our definite integral. Okay, 12 is another one I think you can get through. We want the value. So anything above is positive, anything below is negative. We're going to go from a -1 to 4. You can find those areas, add them up, positive above, negative below, add them, you should get 2.5. So that you can do. Don't need to walk you through that one. 13, the flow of oil in barrels per hour. It's important, so that's our unit here. Through a pipeline on July 9th is given by the graph shown above. Of the following, which best approximates the total number of barrels of oil that pass through the pipeline in that day? So if we're going to be going from barrels per hour to barrels, if we think about these words, we are basically hanging out at a velocity. That's what this is. This is like a velocity graph. And if I'm going to go from barrels per hour to barrels, that would be a position idea. So to go up from velocity to position, then we would have to integrate this, find the area. So if we look at this, this is a rectangle for the most part at about 600. This rectangle would be 600. This rectangle would be 600. This rectangle would be 600. Every rectangle is 600. This graph, as we follow it through here, is basically cutting that rectangle in half. So we would say this is about 300. This is about 300. Add all those up, should give you 3,000. Again, understand your units when we do area. This has we're just doing rectangles right now, base times height. That should be an h. Our base for all of these is, in this case, 6 hours. We're multiplying it by our height, which is barrels per hour. So that produces the unit of barrels that we're looking for. Okay, 14, you're given, again, a function. It's another one where your subintervals are not the same. So you just need to make sure when we do this, this is the most common one. You have to set up your trapezoids separately. So here's our trapezoid, trapezoid, trapezoid. and we have to set them up separately. So you do 1/2. Our first change in x is 3. The bases would be 10 and 30. Our second change in x from 5 to 7 would be 2, and those bases are 30 and 40. And then 1/2, our final change in x from 7 to 8 would be 1. And then we would do 40 plus 20. That's a 40. At least now it is. Throw that into the calculator, add those all up, should give you 160. 15. This is something that they do sometimes you want to be aware of. We did it with our graphs. We didn't do a whole lot with the table, once or twice, so make sure we're just aware of this. Where you're given an acceleration table, so position, velocity, acceleration, and that's what this is, acceleration. The question ultimately is going to ask you, approximate the value of your velocity at 6 seconds. You're going to do that using a left-hand Riemann sum. What we haven't done a lot of with these is they tell you at the beginning of our time, we already have a velocity of 11 feet per second. So if we go ahead and set up our left Riemann sum, and these, if you look, the subintervals of equal length, so 0 to 2, 2 to 4, 4 to 6, they all have equal length. So we can go ahead for rectangle number 1. So this is number 1, and we're doing what? Left endpoint. So for rectangle number 1, its left endpoint functional value is 5, the base is 2. The left endpoint functional value for the second one is 2. The base is also 2. And then for the third one, our functional value is 8. And our change in time is 2. So if we went ahead and just did that part of it, that would give us what? 30. But what this has just given us, what this is the approximate change in velocity from 0 to 6 seconds. Well, we don't just want the change in velocity. We want to know what is our velocity at the end. That's the question. Find the value of the velocity at the end. And so if you remember, at the very beginning here, we already had a velocity of 11. So what we would want to do is take this 11 and add it to the accumulated change. So if we were already going 11, we increase by 30. Our answer would then be 41 feet per second. Okay, 16. I'm trying to remember if we did this. I know this is in our notes. It's always the last question in a set of notes. Hopefully we got to it. If not, something we want to be able to understand. It's kind of, again, a big picture idea. It ties a lot of this stuff together. So if you read through this, they're going to tell you that you have a function, first derivative, second derivative are all positive on a closed interval. So what that really just tells you, let's say this is A, this is B. If the function is positive, you're above the x-axis. The first derivative is positive, you're increasing. Second derivative is positive, you are concave up. So it's going to look like this. Then they're going to tell you that U is going to be used to compute an upper sum. L is your lower sum. T is your trapezoid rule. And then I is your integral. And then they want you to put these into order. So let's break this up into equal subintervals like they tell us. We're going to do 2. So we're going to go from here to here, and then from here to here. So the trapezoid rule is easy to understand. If we went up, hit the curve, these two places draw on our line connecting them, we have our 2 trapezoids. The integral is the exact area, so the integral is really the curve, because that's what we would use to figure out the exact area. The upper sum and the lower sum, what we want to understand is these are the 3 ways, rectangles, upper, lower, and trapezoids, that we approximate an exact value. So the integral is exact. These are our approximation methods. So the upper sum is alluding to our right endpoint rectangle, in this case, or circumscribed, I should say, which just happens to be right endpoint. So let's draw these in. The lower sum would indicate we want our smallest area with our approximations of rectangles and trapezoids, and then that would be our inscribed rectangles. Let me try to draw in inscribed here. It's a little messy. Put them into order. So our lower sum, the smallest area value that you would have come up with, would have been the inscribed rectangle, which is our lower sum. That's why L is the first choice in all of them. The next smallest area would be the actual curve. That's the integral, so I. So it could be D or E. And then we just have to determine what's the next area. That would have been our trapezoids. And then the upper sum is the circumscribed, so it should be D. Okay, moving along. Next page. 17 is similar. This one I know you have not seen. It says, let f be a function with no points of inflection on the interval a to b. If the definite integral from a to b, if you are told that the integral of f is greater than your trapezoidal approximation, which of these could possibly be true? So it's kind of a process of elimination a little bit. Let's do A, and then let's do B. So think about what would happen if our definite integral, which is the exact area, is greater than our trapezoid. Let's say I drew in a line. So just draw a line from A to B. If we went ahead and compared the exact value with the trapezoid rule, what we would hopefully understand is if I drew a trapezoid in here, compared it to the exact area, they're going to be equal. The trapezoid rule and the exact area are going to be the same, so we don't want A. B, if your function is concave down on the interval of A to B. So maybe I should have wrote that smaller. If I draw something that's now concave down, like so, the trapezoid rule, B is actually, we want to be concave up. So let's draw on something that's concave up here. So our graph is concave up. So if that was our graph, here is our real area. Is our real area going to be greater than our trapezoid rule? That answer would be no. If we do C, let me try to draw this over here now. So this will be A, this will be B. Draw on something that's concave down from A to B. So let's draw on something that looks like this. That's our real area. If I now draw in my trapezoid, the area underneath the trapezoid would be less than the overall area, and that's what this is asking us to find. So it would have to be C. All right, 18, another one of these. Again, pretty critical you know how to do these, but it is pretty straightforward. It's one I don't think I necessarily need to go through and show you. Functions, you know, you're going to do a Riemann sum, you're going to do midpoint rectangles. So now when I just do 6 minus 0 over 3 to get this width of 2, now that you're going to be using the midpoints, we want to make sure that we're using these values as we figure out the area of the 3 rectangles. Okay, so definitely do that. Make sure you should get 3.76. Number 19, this would require you to remember what a natural log graph looks like. So we know the natural log curve is at 1. This would be non-calculator. And then we're going to go over here till 7. So here's 1, here's 7. They're going to ask you to approximate this. So if I were to integrate the natural log of x from 1 to 7 using 3 circumscribed rectangles with equal widths, that means we can go ahead and figure out what the base of all of these is with our change in x. 7 minus a 1 over 3. We're going to go by 2s. So we'd be at 3, 5, and 7. So then we have 1, 2, 3 bases of our 3 rectangles. If we went ahead now and figured out what those guys are, for rectangle number 1, the base is going to be 2 for all of them. And if we drew our rectangle in so that it is circumscribed, that means we'd have to hit with the right end point to cover this first base. We would get a functional value of the natural log of 3. For rectangle number 2, our base is 2. We'd go up from the right end point, move over to 3, so the functional value would be the natural log of 5, whatever that is. And then our third one, we go up from 7, come over. So the functional value is a natural log of 7, and our base is 2. If you look at the answers, they've just pulled the 2 out to give you C. All right, the last 2 pages. I'm going to give you these values just to save a little bit of time because we all know we're going to do this. So I'm actually going to pause you so I can write these in. You don't need to wait while I am doing this, but I'm going to write in what these areas underneath the curve are, okay? You can pause me if you want, copy all of these down. The big red dots are the accumulated change. So this is just telling us that at 10, this is what we started with. At the time of 0, we had a velocity of 10 feet per minute. We know at some point we're going to have to add all these accumulated changes together. So I just did that. I wrote them down. This is our accumulated change. This is what we're going to get at 5 total. At 10, you're going to get a value of 0 overall. When we cross back into the x-axis, you're going to get a value of a negative 10. And then at the very end, we're going to get 15. So what the question is getting at, hopefully you have these now copied, is the idea that when we're dealing with position, velocity, acceleration, they gave us an acceleration graph. So certainly there's going to be a question about acceleration. That's part A. What is the particle's acceleration at the time of 2 minutes? So if we go to 2 minutes, we can just look at this graph and we would see pretty quickly and easily that it's 10, and then this would be feet. Looks like 70, 10 feet per minute squared. But then the rest of these questions, B, C, and then D, all deal with the idea of a velocity. So minimum velocity, when do we change directions? That's a velocity question. When is our velocity 0 and change signs? And then when are we moving to the left, or are we moving to the left or the right? We know if our velocity is positive, we go to the right. We know if our velocity is a negative, we're going to move to the left. So all of these now are velocity questions. So B, what is the particle's minimum velocity? Well, it had to have occurred at either an endpoint. So that's either 0 or 14. If I want to know when does the velocity have a minimum, it would be when the derivative of the velocity is 0. So that could have been over here at 65 or at 5. So those are our candidates. If we look, we've already done the work for it. Our minimum velocity would have been a negative 10 feet per minute. C, what time, if any, does the particle change directions? So if we want to know what time does the particle change directions, we're looking to see when did our velocity equal 0 and change signs. So if we go back up to our graph here, this will let me move it. Come on. I could do that too. Our velocity is 0 right here, and that happened at the time of 10 minutes. And then D is the particle moving to the left or to the right at the end of the interval. If you go to the end of the interval, our velocity was 15, specifically a positive 15. So we would have to be moving to the right, and it's because our velocity was positive. All right. Last but not least, we go to this one. This one I can keep you engaged, hopefully, while I write these down, because these areas are much easier and shorter. It's not quite as crazy. This first triangle has an area of 20. Get that down. This rectangle has an area of 40. Here we have 10, and then this tiny little triangle is a negative 5. Okay, that's a 10. Same idea, position, velocity, acceleration. You are given a velocity graph. So we should be able to now answer any of these 3 things, a position, a velocity, or an acceleration. So in this one, A, at what time, if any, does the runner change directions? Same idea. We're looking to see when does our velocity equal 0 and change signs. So that's going to be at the time of 5. B, what is the acceleration of the runner? So if you were hanging out here at the velocity, which we are, and we want to go down to the acceleration, we need the derivative. The derivative is on a graph or a table. It's our slope. So if we go to 1 second, if we can figure out what is the slope of this line has a slope of up 20, right 2. Up 20, right 2 gives us a slope of 10, and then that is feet per second squared. C is asking you what is the greatest speed attained. Speed is the absolute value of our velocity. We are looking at a velocity graph, so wherever this would have the greatest absolute value would be our greatest speed. So the greatest positive velocity we have is up here at 20. The greatest negative velocity, or the most negative velocity, is down here at this negative 10. So between 20 and a negative 10, the one that has the largest absolute value would have been the 20. So our greatest speed was 20. And then D and E, distance versus displacement. Those both require us to do, if we're going to go upwards, we want to do the integral of our velocity. The integral, again, accumulates change. That's the big picture item walking out of here today from this packet. If we need to accumulate change, the integral is what does that for us. So it's going to take us from velocity to a position. These are both positions, distance and displacement. If you remember the distance, we want to integrate the absolute value of the velocity. The displacement, we want to just integrate the regular old velocity. We've already done that above. So if we go through here, what just happened there? Oh boy, I'm not sure. Let me try to undo that. There we go. We have what, 60, 70 above, and we have a -5 below. So if we come down here and answer the distance question, the absolute value of all of that, our distance would have to be 75. If we just want the net change, which is our displacement, then we would get 65. 70 plus a -5 is 65. Okay. Hopefully that makes some sense. This is one of the, I think you're going to get a sequence and series question for sure. And then them giving you a table, it's really going to be a table if they give you one of these questions, and they're going to have you do, what's the slope of the table? What is the accumulation of change of the table? So you're doing your trapezoid rule, your rectangle, really, really common. If we were doing a full 6 questions like we normally do, this is one of the things I tell you for sure you're going to get. You can look through some old AP questions online, and you're definitely going to find plenty of these if you want to see if you can get through some of them. So with that, I'll bid you adieu. Have a good weekend, and we'll see you guys next week.